systems. So I called it this way. Okay, vibration of translational or translational system. Okay, which means that a system that can be modeled as a spring and mass system. So either we have a spring mass system or an actual system or practical system other than spring and mass, you model it to a spring and mass. Okay, so we have the model we are going to use is a massless spring carrying a mass at the free end. Okay, and we saw last time that if you have arrangement of springs, either if they are in series or in parallel, then we can add the springs accordingly, and then come up with the spring mass system with a spring stiffness equivalent. Okay, so here we have in general if there are two springs in series or two springs in parallel, or you can extend the number of springs more than this. Okay, as well as we mentioned before, equivalent stiffness. If you have a rod or beams. Okay, so some of the things we have here maybe we didn't reach to, like the torsion of shaft, which is shown here after the above the helical spring. Okay, so let's see the tutorial from beginning. Question number 1, we have 0.14, 0.453 kilogram mass attached to a light spring, elongates it 7.87 millimeter. Determine the natural frequency of the system in cycles per second. We have the mass is given, and also we have the deflection is given, or the statical deflection. So it means that you have a spring, light spring, which means massless spring. When the mass is added on the spring, it will elongate to equilibrium to 7.87 millimeters. So we take this as delta, and then we can find Fn from the equation is 1 over 2 pi square root of g over delta without using the mass. Okay, if you want to use the mass, it means you have to find k first from the equilibrium equation, which is k delta equal to mg. Okay, so the mass is just saying that there is a spring mass system. And if you can add, like find k, for example, you can find k from k delta equal to mg. Okay, this is one equation that you can find k from here, and then you can find f. Okay, so we call it fn. Question number 2, a spring mass system K1 and M has a natural frequency of F1. If a second spring K2 is added in series with the first spring, the natural frequency is lowered to half F1. Determine K2 in terms of K1. Okay, here we have two systems which are with known natural frequencies. Okay, this is F1 is just a number, but it is called F1 because K and M are just given as parameters. F1 is the natural frequency of the spring mass system. So you have two systems here. The first system is when it consists of spring of a stiffness K1 and M. So you can just represent this. as M and K1. The natural frequency is equal to F1. This is what is given. The second system is if a second spring K2 is added in series with the first spring, the initial frequency is lowered to half F1, determine K2 in terms of K1. So it means there is a second spring, a second system. Okay, this is the first spring with the stiffness K1. Another spring with the stiffness K2 is added in series with the first spring. And then this is the mass, the same mass. The initial frequency here is half F1. Okay, so suppose K1 and M are known, find K2 in terms of K1. This is the problem. Okay, so you can just label this as number 1 and this is number 2. And find, in order to solve this problem, you can find the expression for F1, okay, and the expression for F2, for half F1, which is the second natural frequency of the second system. Or I mean the natural frequency of the second system. For the first system, this is our model, the one we did in the lectures. Fn is 1 over 2 pi square root of K1 over M. Okay. For the second system, we need to get equivalent system because we have two springs in series. So for system 2, you need to get K equivalent, same mass, and you get K equivalent. K equivalent is K1, K2 divided by K1, K2. Okay, because this is those two springs are in series. Therefore, the natural frequency is not going to change. This is the natural frequency is the same. Okay, it is half F1 as given, but now we can get the expression of Fn is 1 over 2 pi square root of K equivalent divided by M, and K equivalent is K1, K2 divided by K1 plus K2 divided by the mass. Okay, so we have two equations with two unknowns. Okay, and the question is to find K2. Okay, so you can relate the two equations. We have F1 equation. You can substitute for F1 here, and then you can simplify to find K2. Okay, so this will be 1 over 2, and F1 is from the first system is 1 over 2 pi square root of K1 over M. And this is in fact equal to the natural frequency of the second system, which is 1 over 2 pi square root of K1, K2 divided by K1 plus K2 M. Okay, you can simplify that, you know, square root of K1 over M will cancel out with square root of Km here. You can see they cancel out. 2 pi and 2 pi cancel out. Then what you will have is 1 over 2 on the left hand side, and square root of K2 divided by K1 over K2. And this can be solved for K2 because there is only one unknown. K2 is the unknown. Squaring both sides, we get 1 over 4 equal to K2 divided by K1 plus K2, and then you can solve for K2. So K2 is equal to 1 over 3 K1. Okay, so the idea is that we have two systems, but they are given as they are related with the nature frequency. That is, the second system has nature frequency is equal to the nature frequency of the first system divided by 2, which is half F1. And that the second system consists of series of springs. And then you can simplify it this way. Okay. Question number 3. A mass M is attached to a core that is under attention T, as shown below, assuming that T remains unchanged when the mass is displaced normal to the chord. Write the differential equation of motion for small transverse vibrations and find the nature frequency of a vibration. Now, the chord, this might be according to what we did in statics. Just imagine that this is in statics now in equilibrium. The assumption made here is that the tension in the chord is and assuming that the tension T remains unchanged when the mass unchanged when the mass is displaced normal to the chord. So usually in statics, if you have a chord fixed on both sides, when you add a load, not in the middle, somewhere, okay, or you put a mass, this will go to equilibrium, right? When you put a mass, or just you put a weight. Usually what we did in statics that this will take theta1, say, and this will be under theta2, and then you draw the free body diagram. You will have T1, and you will have T2, and you will have here the weight. Okay, so T1 not equal to T2 because theta1 is not equal to theta2. Okay, in statics, this is not correct, that T1 equal to T2. Okay, now, so why the assumption is valid here, that assuming that T remains unchanged when the mass is displaced, he's even not considering the statics, he said that the mass M is attached to a core that is under tension T. That means T1 equal to T2 equal to T. That's what he's saying in the first line. That the tension in the core after adding the mass is T. And it will remain T even during vibration. Okay, we know that in vibration, theta1 and theta2 will change. So accordingly, T1 and T2 will change. But also is saying this is another assumption that the tension is not going to be different than what it was in statics. Okay, so first of all, in statics, how do we know that, or this assumption that the tension is the same? By knowing that the mass is light, or that the deflection here is very small, theta1. If you take theta1 very much less than 1, okay, this is less than means very much less than 1, and theta2 very much less than 1, then you can say that T1 equal to T2 equal to T, even in statics. Okay, in statics, if you recall what we did is that we take the angles as 30 degrees, 60 degrees, or 45 degrees, right? Those are even 15 degrees, 20 degrees. Those are relatively large angles. Okay, and here we are talking about vibration. That means about the equilibrium position. So this is the equilibrium position here. And that this deflection is small. Okay, you can say this is Y. But this is small, that you can assume that the tension in the cord is not changing with vibration, and that the tension is high. It's not allowing that the sag in the cord. You know, if you have this is in against gravity, and if you have this cord, and this is gravity is downward G. Okay, if you put a small force, this will sag. Okay, if you put a mass M, it will sag. Okay, this sag or deflection okay, under high T, you need, of course, infinite tension to make this straight. You know, equilibrium position to be horizontal line, it means that the tension is infinity, which is cannot be accomplished. But we can assume that it is high enough that the sag is very small, it can be neglected. So only considering the changes in the that happens during vibration. Okay, you can see what we are doing is to come up with a model same as the spring mass system, which is a single degree of freedom. But in fact, this is more than single degree of freedom. If you consider the weight of the cord, you consider the sag, you consider the changes in the tension, and that becomes a completely different problem. But the assumptions we are doing makes the problem as a single degree of freedom. Deflection is very small. Okay, you can neglect it under static. Okay, this is one of the things under high tension T. Okay, if T is low, then it will sag. But if T is very high, the deflection will be very small that you can neglect. Okay, one more thing to look at this problem is that we are looking. This is, as you can see, G is downward, right? Gravity against gravity. You can look to this problem from the top view, top side, from the top view, which means you don't see the gravity is not part of the free body diagram. Okay, you don't put the weight here. Okay, so you can consider this as a top view, not a front view, where gravity you can see it is downward. There is no gravity here. Okay, this is horizontal. Okay, top view that shows horizontal plane. Okay, this is not the vertical plane. If this is vertical plane, it means you can see the mass is moving up and down. But if this is the top view or horizontal plane, you will see the vibration sidewise, right and left, not up and down, right and left. So that gravity is not part of the free body diagram. Okay, so either you can assume that the deflection is very high, very small under the very high tension T, or you can think of this as a horizontal plane, that the cord is vibrating in the horizontal plane. Okay, and then you keep the tension to be the same. Okay, this is in general, T1 is not equal to T2, but in this case, we can assume that T1 equal to T2, equal to T. So the free body diagram becomes, if you take, and this is theta 1, and this is theta 2, and the tension T here, and the tension T here. Okay, if you want to make T1 equal to T2, no, I mean, just name them T1 and T2, we can prove they are equal with the assumptions we are saying for that theta 1 and theta 2 are very small. Okay, so let's say that they are T1 and T2. So we have the horizontal, they make angle theta 2 here, and T1 makes theta 1 with the horizontal. Take this sum of forces in the x direction. We will have T1 cosine theta 1 minus T2 cosine theta 2, okay, and then for theta 1, as we said, theta 1 very much less than 1, cosine theta 1 is 1. And the same, similarly, theta 2 very much less than 1, cosine theta 2 is equal to 1. Okay, now we are not talking about theta 1 and theta 2 in degrees. They are in radian and in small numbers in radian. If you put this in the calculator, change the mode to radian, and put some angles, small angles, you can see that cosine theta is the same. I mean, this is by using the expansion, Taylor series expansion. The Taylor series expansion is that cosine theta 1 is plus 1 plus theta 1 square over 2 factorial, and so on. So this is, if theta is very small, then theta 1 square is even smaller, and you can ignore this. Ignore the higher order term, becomes just 1. The same thing with cosine theta 2. If theta 2 is very small, then theta 2 square is even smaller, and then you can neglect the higher order terms, and then you have cosine theta 2 is 1. Which means very close to 0. I mean, this is why cosine 0 is 1, right? So if this is very close to 0, it means cosine theta is 1. And if cosine theta is 1, this will reduce to that T1 minus T2 equal to 0. Okay. And that means T1 equal to T2 equal to T. So what we can do is only find the equation in the y direction. Okay, the y is upward positive, so this is minus t sine theta 1 minus t sine theta 2 equal to m y double dot. And from here you can proceed to see that this is the equation of motion of a single degree of freedom system. Now what is sine theta 1? As I said, this is y for the transverse displacement from here to here is y. Then you can construct right angle triangle, right? Here and here. So sine theta 1 is the opposite over the hypotenuse. So it is y over a. That's sine theta 1. And sine theta 2 is y over b. Okay, so you can replace, substitute for sine theta 1 as a over y, sorry, y over a minus t times y over b equal to m y double dot. So you are getting equation for y. Okay, so I'm adding, I will take this to the other side. The first two terms, I can take ty as common. So this becomes ty multiplied by 1 over a plus 1 over b equal to 0. Okay, so my double dot plus, when you add 1 over a plus 1 over b, this will give us a plus b, which is L, divided by AB times T times Y equal to 0. Okay, so finally y double dot plus TL, which is A plus B is L, over AB times Y equal to 0. So the assumption we did that T is constant, already L is constant because this is an extensible cable, and A and B are constants also. Okay, so this will be like representing TL over AB is as K. Okay, and M, of course, is the mass. When you divide by M, you get Y double dot plus TL over ABM, okay, times Y equal to 0. Okay, this is the final differential equation in the final form. I mean, in its final form. So the natural frequency omega n is equal to the square root of this. Okay, so that's the natural frequency. Okay, it is given that omega n is square root of LT over AB n. Okay, so this is a problem that is not given as a spring and mass, but modeled in the same way. You can, with the final equation we reach to, you can create a spring mass system. But K is given as TL over AB, and you can change those values. It means you are changing the value of K. Okay, but this is the same equation. The differential equation is same as the equation of the spring mass system, which is second order ordinary differential equation with constant coefficient, and it is homogeneous for free vibration. Okay, all the parameters here are constant. The mass, the length of the cord, the position of the mass A and B, and the tension in the cord, which is the assumption we did.
دكتور
Yeah.
شلون خلينا ساين ثيتا تساوي y over a.
Okay, the sine theta is for small angles also equal to tan. Okay. Yeah. Also equal to. Here we have the cord. This is located at A, and it is inextensible, so this part is also A.
تمام. يعني ما يحتاج نستعمل نظرية فيثاغورس عشان جذر وهذا ما.
لا ما يحتاج. يعني already this is assumption. This is assumption that sine theta is equal to tan theta equal to theta. So this is like arc. You take this as an arc. So theta times A equal to Y. The same thing here. Theta 2 times B equal to Y. In the same thing.
تمام.
Okay,
دكتور.
question. Yeah.
ليش دكتور في الايكويشن مال الفورس along the y direction ما اعتبرنا الام جي لتحت؟
Okay, ما اعتبرنا ال mg. This is the same thing we did for the spring mass system. We didn't put mg here because the vibration is about equilibrium, and that it will cancel with the static problem with the equilibrium equation. Okay, this is one thing. The other thing is, as I said, you can think of this problem as tube view, in which the vibration is occurring in the horizontal plane, so that weight is not part of the free body diagram. Okay, even if you consider this is vertical plane, the vibration is about equilibrium position, and which means that the weight is already considered in the tension. That makes the system in equilibrium. Like the weight and the spring was K delta during equilibrium, and they cancel each other. So you can think of this problem on two ways. Either that the vibration is about equilibrium and that the weight is already cancelled by the tension in the cord, or that this is the system is arranged in the horizontal plane in which the weight is not part of the free body diagram. The weight is perpendicular to the view you are seeing. Perpendicular. So it is not along the y direction or the horizontal direction. It is perpendicular to the plane. Okay, question number 4. A schematic diagram of a system with two springs is shown below with the following data: K1 equal to 1000 Newton per meter, K2 equal to 2000 Newton per meter, and the mass equal to 2 kilograms. Show on the given schematic diagram the independent variable, يعني direction of X, with the indication of the positive direction. Okay, so just to practice on labeling things. Okay, this is the system, and you take the positive direction. Okay, you put this X. Okay, this is what is required. Draw the free body diagram on a separate graph. Just, you put the mass and put the forces. Okay, the force, with this assumption we did that X is positive to the right. Okay, this is X. The tension and the spring on the left is under tension, and the spring on the right will be under compression. Right, so the force of the spring on the left will pull the mass to the left, and the spring on the right will push the mass to the left as well. Okay, the spring force is, by Hooke's law, is K1 times X, and this is also K2 times X. Find the equation of motion is obtained by using sum of forces equal to mx double dot, which is a Newton's second law. And the direction, positive direction of forces is to the right, because the positive direction of X is to the right. Then we obtain the initial frequency. Okay, you can solve A to B, A to C this way, or you can think of the two springs, they are arranged in series or in parallel. Okay, the springs are in parallel because they have the same deflection. And this is fixed here and fixed here. And at the other point, the spring K1 is moving with X. The spring K2 is also moving with X. So they are in parallel. So K equivalent is K1 plus K2. And the initial frequency is square root of K equivalent over M. So the model to this is just one spring with one mass. Okay, and the K equivalent is K1 plus K2. And then omega n is square root of K1 plus K2 over M.
دكتور
Yeah.
أعتقد الشاشة مشيرة، الشاشة واقفة عندي.
الكل كذي لأن أنا عندي يبين إن هي شغالة.
ما قاعد نشوف دكتور كلنا.
اوكي ما يعني انا مسوي شيرنج
الحين أشوف.
تبين.
اوكي ما ساعات يمكن من الانترنت. اوكي الحين تشوفون لا فهو لأن عندي يبين I can see it is the border is red. It means it is in the share mode. Okay, so this is the if you move on with the answering the question, this is the free body diagram. And then this is the equation of motion. using a Newton's second law. And then, of course, when you complete the equation of motion, you can find the nature frequency from without solving. All what we did so far is not solving the equation of motion to find the response. We are finding only the frequency or the period of oscillation. Okay, or you can think of the two springs are in parallel, and then the equivalent system will be a spring and mass with K equivalent equal to K1 plus K2. And of course, this, both approaches are correct. Question number 5. A given system of unknown mass m and spring constant k was observed to oscillate harmonically in free vibration with the natural period tau equal to 2 pi times 10 to the power minus 2 seconds when a mass. So we have a spring mass system with mass m and the stiffness of the spring k. The period of oscillation for the system is 2 pi times 10 to the power minus 2 seconds. When a mass m equal to 0.9 kilogram was added to the system, see the figure below, the new period rose to 2.5 pi times 10 to the power minus 2 seconds. Determine the system parameters m and k. This is what you see here is system number 2. When m is added, this was added equal to 0.9. But system 1 was spring and the mass. Okay, this is the first system. With tau 1 equal to 2 pi times 10 to the power minus 2 seconds. For the second system, tau 2 equal to 2 pi times 10 to the power minus 2 seconds, 2.5. Okay, there are two unknowns here, k and m, and you can find those in terms, you can find their values, k and m, because we have two equations, two unknowns. What is the equation for tau 1? It is 2 pi over omega n, and omega n is square root of k over m. It means this is square root of m over k. And the second system, tau is again 2 pi over omega n, but the mass is now increased, so it will be m plus m over k, with m here is known, equal to 0.9 kilogram. Okay, and you solve two equations with two unknowns. We should be able to find the value of k and the value of m. Okay, and question 6. This is about dependent motion. A weight W is supported by 3 frictionless and symmetrical pulleys and a spring of stiffness K, as shown below. Find the natural frequency of the vibration of weight W for small oscillations. Here, it is pulley arrangement system, but there are 3 chords. This is chord number 1, which goes from ceiling to the center point of the second pulley, right? This is one chord. And we have a second chord, which goes from the ceiling around the second pulley to the third pulley, center of the third pulley. And we have the third chord, which goes from the ceiling around the third pulley to a spring here. Okay, those are 3 chords. Now the assumptions we did, there was an example we solved in maybe one of the lectures before, that the assumptions we did, even though they are not mentioned, but we have to use those. Yeah, that's frictionless is saying 3 frictionless and massless, which are those are the 2 main assumptions. So there is only one mass, which is here, the weight. This is moving with X. So what you need is to get equivalent system of spring, K equivalent, and M. M that is moving with, or the weight here as given, moving with X. Okay. The assumptions I added that the chords are massless and inextensible. So you need to find the equation for each chord in order to get the dependent equations motion, or this is dependent motion, and you need to get the dependent relation through the kinematics. Okay, so for chord number, you give datum and location for position for each pulley, for each block here. This is the datum. Okay, datum is here. Then you can give the location of the center of the pulley as x1. Okay, this point of the center of the pulley is moving with x1, which is same as the weight. I mean, that is only x1 plus some constant. This is a constant here. So in fact, the pulley, this pulley, and the weight are moving without any relative displacement, so that they can be considered as one object. Okay, the weight and this pulley number one is one object because this is a rigid link. Okay, so usually we don't give, so this is a rigid link. So that this pulley number one, and the weight is one object. This is pulley number two, and this is pulley number three. We don't have more. Okay, with the rigid link, with the pulley number one and the weight is one object. So if you find x1, it means it is also x for the weight. Okay, so the positive, the position of pulley one is x1. The position. Okay, and just move this away. Okay, this is x1, and the position of pulley 2 is x2, and the position of pulley 3 is x3. Okay, as we said, the chords are inextensible, but here we have flexible element, which is the spring. The spring is zero deflection here at the datum, and it is moving at any point is moving, right? So what we need is the other point of the spring. The other point of the spring is moving with different than x3, so you can call it x4. Okay, so the other side of the spring, or the other end of the spring, is moving with x4. It is not moving with the pulley, right? Because the pulley is also moving up and down, or if this is an equilibrium, it is moving downward. So it means that the cable is the other side, the other end of the cable, which is this point, is not same as x3. Okay, the position is different. Okay, so let's say that the cable or the cord will end up here. Okay, this is the end of the cord. And then you have the spring. Okay, for the spring, you need to know the deflection in the spring in order to find the force in it by using Fuchs law. Okay, what you need to do is for each cable, for each cord, you find the length of the cord so that you use the relationship to get the kinematics relationship. So for first cord, L1 equal to what? Any clues? Any clue about this? The length of the cord, number one?
x1 plus x1 minus x2.
Excellent. X1 minus X2. Okay. And L2 is
x2
yeah,
plus x2 minus x3.
and the last one is L3 equal to X3 plus
x3 minus x4.
okay, excellent. Okay, those are the actual length. Of course, plus let's say C1 plus C2 plus C3. Okay, the constants are around the pulley, around the pulley, around the pulley. Okay, that is not considered, but just to be more specific. Okay, now the change in length is what I need. What is the change in length? I need x1, I need x2, I need x3, and I need x4. So the equations, delta L1 will be 0. It means that x1 plus x1 minus x2 equal to 0, which means that 2x1 minus x2 equal to 0, or x2 equal to 2x1. Right? Since we are looking for the change in position, not the actual position of the pulleys. And this will lead to that x3 equal to 2x2 and that x4 equal to 2x3. Those are the kinematics equation. Okay, furthermore, we need to find make back substitution. Okay, so that x4 equal to 2x3. x3 is 2x2, right? And x2 is 2x1. So this is 8x1. And the next thing, this is the important relationship. I'll just change the box color. x4 equal to 8x1. The other thing you need to do is the free body diagram for the rigid link will carry the weight. So this is the weight, and the link will have the weight. And if you take the pulley and the free body diagram of the pulley, it means there will be weight here, and the tension in the cord will be W over 2 and W over 2. Okay, and when you consider this free body diagram for pulley 2, this will be W over 2, and here it will be W over 4, W over 4. And when you go to the third pulley, this means that we have W over 4 here, and this will be W over 8, and this is W over 8. Then what is this? The spring force from Hooke's law, or before that Hooke's law? This is the equilibrium point, or the connection between the cord and the spring. Then the force in the spring is also equal to W over 8. Okay, so we have force in the spring equal to W over 8. The force in the springs from Hooke's law is K times X4, the change in length, not the capital X, the small x, equal to W over 8. And x4 is 8x1 equal to W over 8. Put W on one side. This will be 64K x1. This equation, it means that the weight equal to K equivalent times x1. Here it is x1. And then the natural frequency, once you reach to this, therefore omega n equal to square root of the K equivalent, which is 64K over M, or it was W over G, given using the same parameters. Okay, so the initial frequency is 8 square root of kg over the weight. Okay, the time is already, we consider, we solved the question 7, then we have just 2 more questions. We will do this next time. Okay, any questions? Okay. See you next week.
مع السلامة دكتور.
That's it.